Good afternoon. I just want to clarify two things. When Bary asked if I would talk, he didn't say I'm going to have to follow Babichenko. So, second thing, I should have given this talk yesterday because it's much more about axiomatization of Nash equilibrium, which was the topic yesterday, and related material. But Liat, I think, cited Nash, and I want to correct the impression that I had, and that is, the first time I met Nash was a conference in Jerusalem in honor of Auman's
95, yeah, in 95. Yeah. Auman's 65.
65th birthday, and John Nash came, and he was very timid and Nash, and I read his papers all my life.
Even more than usual.
So he was, and we are sitting in breakfast in the hotel over there that everybody gathers, and everybody is talking about Nash equilibrium of this auction or that auction, and he comes down the stairs and he sits next to me and he listens to this discussion. What is the Nash equilibrium of this and that? And he bends over and he says, I don't understand, what does Nash equilibrium have to do with auctions? So there was a really interesting, so it's a good story, and it's a true story, I'm not making it up. So the other thing is I added here the footnote because that was influenced by Auman's lecture that he gave recently. He said, if you want to understand how people behave, don't give them artificial examples. Look at how they behave in real situations. And he was talking about experimental economics then. So I'm going to try to do some examples based on real games that people play now, not imaginary, artificial. So I'm talking about equilibrium resilience in current applications of game theory. I'm going to talk about the notion of equilibrium resilience. And I kept saying it's a simple measure that explains a lot, and I took simplicity to be a virtue in the sense that Peyton was describing yesterday. But ChatGPT doesn't like simple. It thinks simple is stupid. So it corrects me to say straightforward. Okay, so it's a straightforward, simple, whatever you want. It's a straightforward notion of stability that explains things. And if you can explain them simply, that's better to me than if you go through all kinds of very complicated refinements and so on. So for example, the best example maybe is that price competition, people sell at the cheapest competitive prices. It's not a dominant strategy, but you can explain it simply by resilience arguments. On the negative side, we know many examples. I'm not going to take the time to do them, but supply chains, centralized production, dictatorships, and all these things are considered unstable for reasons that are very much agrees with equilibrium resilience, because you can easily disturb such equilibrium if it depends on if its resilience is low. And I'm going to focus mostly on normal form games, because to talk about defections in normal form game, it's very clear when somebody defects. When the game starts being involved in highly extensive form games and where you defect at sub-game that you wouldn't have let the game go there in the first place, it's not clear if this is a real defection or not. So I want to leave it in the simplest case in normal form games, and I'll give you an example of why this makes a big difference. And I'm not the first to talk about equilibrium resilience. I was very surprised way after I was into this research that Jean-Jacques Rousseau and David Hume in the 1700s talked about resilience. They didn't call it equilibrium because it was way before, 200 years before us. They talked about social contracts, which was their word for equilibrium, and defection from social contract, it's resilience to Nash equilibrium. And 200 years later, Schelling started formalizing it, and Schelling was really wanted to show people that externalities are really captured by n-person games. So he took an example of computing, and what did he pick? He picked resilience, which is exactly what I'm going to do here. So he was the first one in a formal presentation to do that. And then Elias in 2002, and then 4 computer scientists looked at implementation problems and showed that if the resilience is high, you can do much better implementation than normally we can do. If you cannot do dominant, you can do a very good dominant-like implementations. And various people pointed me to these papers over the years. And then the paper I'm going to talk about a lot is a paper I have with my co-author and son, Ehud Kalai, and we have an axiomatization of resilience of all possible equilibria, which I'm going to use in this presentation here. So let me give you an example of what I mean by resilience and why I think it's important. So let me look at simple price competition. So I have 100 producers who produce exactly the same good. They're all going to the same market. They're all going to sell it. And let's imagine that each one costs, the cost of production for each one is a fraction of the dollar. And each one has to post a price. I'm going to sell it for $1, $2, $3, and so on. So it's a game because how much money, and a buyer is going to buy and buy from the cheapest seller. Let's assume that. So if a buyer is going to buy from the cheapest seller, and I have to post a price, I want to be the cheapest seller, and then you can easily see that posting, if I'm allowed to post at 1, 2, 3, or any number of dollars, everybody posting at the price of $1 each, price competition, everybody posting at the lowest profitable price is a highly resilient. And in what sense do I win that? In two senses that I'm going to discuss it. So first, I'm going to say, look at this game. If any two producers, if Yuval and I decided to sell for it $1, then the rest of the sellers will have incentive to sell it. Not only the rest, Yuval and I, each one of us will have the incentive to sell for $1 because it will be incentive compatible for the two of us to do that. And the rest will follow also. So if two producers post a price of $1, then everybody wants the price at $1. And in that sense, I'll say that in this talk, that the critical mass of this equilibrium, everybody posting for $1, is 2, because it takes 2 people to start to formulate this equilibrium in this sense. So it's a critical mass is 2. And you can look at it from the other side, which is equivalent, kind of obvious once I put down the formal definitions. If, let's say that all 100 of us posted $1, the equilibrium, if up to 98 people change their mind and post for more than $1, it still will be everybody's best response to post at $1 despite this deviation, including the deviators. They would say, I'm sorry, I raised it above $1, and they consider it's related to the critical mass being 2. So in that sense, I'll say that the resilience of everybody posting at $1 is 98 because it withstands a defection of up to 98 people. So these are the simple measures that I have in mind. So the example,
not 99.
What?
And you want to say, but not 99.
Not 99, up to 98, yes. Thank you. Oops, what did I? And you can see that the resilience and critical mass are complementary, dual. They add up to the number of players, so it makes it very nice. So even though the relationship is so directly connected, in applications, one may be more natural than the other because the critical mass suggests how many players you need to form an equilibrium, where the resilience says how many defectors it can withstand. So I'm going to talk about the resilience measure, and it's going to be in units of players, so it's going to be 0, 1, 2, up to n-1. You don't need to go to n, you'll see why. The resilience levels are essential for predicting reliability of an equilibrium, whether it'll be played or not. And I'll review the theory, definition, applicability. Then I'll talk about implementation, where this is, to my knowledge, a new implementation method using high resilience that you couldn't have done just with dominant strategy, but it's close to as powerful. Time permitting, we'll talk about participation games, and in particular, stag hunt games. They are the cornerstones of stability, and I'm not sure if it goes to Jean-Jacques Rousseau or later philosophers. The name Jean-Jacques Rousseau always comes here, but stag hunt games are the cornerstone of stability if you look at the proof of our main theorem. And then the question is, how are these related to refinements? They are different from refinements, even evolutionary stability, I think. So here is the general definition for normal form games of critical mass and resilience. So the resilience of a profile of strategy is sigma in a game gamma, and Rida did a great favor to me. He emphasized the fact that if you talk about sigma, you talk about sigma in which game. You don't say the bottom left of a bimatrix game is in equilibrium. Say the bottom left is equilibrium of this payoff table. So it's, whenever you talk about a profile of strategies, in what game? So if I talk about the resilience of sigma in the game gamma, it's the maximum number of sigma defectors that sigma can withstand. And what do I mean by that? Sigma withstands d defectors if at any profile that you can get from sigma by d defectors from sigma, create a new profile theta, it still is everybody's best response to play sigma. Does that make sense? So if you look at the defection scheme, the defectors wouldn't want to defect because their best response is to come back and play sigma. And by them, even when they defect, nobody would want to defect. So the largest number that the equilibrium can withstand is the resilience of sigma. And dual to this is the critical mass. It's the minimal number of sigma players, let's call this number P, that form sigma. If P players play sigma, then it is best response for everybody to play sigma. So if you look at the partially formed equilibrium, where only P players chose to play sigma, and everybody else, they have to choose to stick with their choices, and everybody has to decide whether to join or not, it's still everybody's best response to join sigma, and that's the number, the critical mass. Any question, please feel free to. And withstanding sigma defectors is exactly what we mean by Nash equilibrium. If there are no defectors, your best response is to play sigma. That's what Nash meant. Only you can do better. And that's one question I wish Nash was here. I could ask him, did you know it? And he just didn't want to throw in too much confusion early on, or is this really something? So withstanding 0 defectors is a Nash equilibrium, but you may be able to withstand the 98 defectors and still have the incentive to play sigma. And withstanding defectors and formation are monotonic. If you withstand 5 defectors, you will withstand 3 defectors, and if 3 people can form the equilibrium, then 5 people can form the equilibrium. And in modern terminology, P players form sigma if it's not just it's incentive compatible, it's uniformly P incentive compatible. Any P players will make it incentive compatible for each other, no matter what the other players play. So it's uniformly P incentive compatible. And you can see the duality very easily, because if you write the 2 definitions side by side and you look at the conditions, any profile with D or fewer sigma detectors, sigma defectors, sigma I is P optimal for every player. This is the same condition if they add up to N, any profile with P players, if P equals N minus sigma, N minus D, then it's exactly the same condition. So it's whether you state the condition on the number of defectors or state the conditions on the number of P players. So it's no surprise that the 2 notions are dual to each other, complementary.
So Ehud, as I recall, you're not assuming that the game is player symmetric. You're assuming...
No, I'm not assuming not, definitely. Thank you. Yes. The definitions are written, and I can rewrite the definitions to make it non-symmetric, but it'll take another slide or 2. Yes?
How much power do the defectors have? Let's say
How many powers, what?
power. Like, let's say 2 or 3 defects.
I can't hear. How much power, what?
Do the defectors have?
That's the defectors.
Can they
So it depends how many of them there are.
Can they correlate their strategies?
Yeah, they can do whatever they want. The definition still holds. Whatever they play, however they got to it.
Okay. And,
Thank you.
for each of them, it has to be strictly better, or
Each of them,
sorry, it has to be best response
No, I'm saying whatever they do, and we'll comment on this, that's the difference for refinement. Whatever they do, it doesn't have to be Tremble or Zentlen. They can just say, I'm going to do something else. Can I destroy your equilibrium? So I'm going to use here the terminology of resilience, and that was used by Schelling and the computer scientists, and Adam and I. Elias used the terminology of faulty players. Sigma faulty player is one of the defects from sigma, and fault resilience is this, fault tolerance is the resilience, what I call here. So we can arrange it in a table, and that would be helpful. These tables are faster way to see things. So if I look at an arbitrary n-person normal form game, and I look at all the profiles, however I got to them, correlation, without correlation, or what. So there'll be many profiles of resilience -1, and if you check the definition, -1 is reserved vacuously for things that are not Nash. If you look at the definition, something gets the value -1, sigma gets resilience -1 if it's not Nash equilibrium. From 0 on, all of these are Nash equilibria, but in increasing level of resilience. So 0 resilience is Nash the weakest Nash equilibrium. I will call them fragile, following a suggestion of Vince. And the strongest Nash equilibrium are what we call dominant strategy. And they are also Nash equilibrium, but in the highest possible resilience. So if you look at this table and you arrange everything by resilience levels, they are here. The critical mass is the dual. It's n minus that, so that goes up from right to left. And depending on the arbitrary game, there may exist or not exist profiles that are dominant strategy. They may exist or not exist. By the way, unlike, it was a very good paper on maximization of Nash equilibrium. Was it like, and my formulation of a game can include mixed strategies or not. You tell me what strategies player one has, what strategies other players have. It may include mixed strategies or not. Whatever strategies it may play, that should be not empty, I assume. It may be played or not. So if, for example, if the game has no mixed strategies at all, it may have no Nash equilibrium whatsoever. So for example, the game may be match pennies with no mixed strategies, in which case there are no Nash equilibrium, right? Or the game may be such that there are dominant strategies in it, or there are not. So any one of these may exist or not exist, depending on the game under consideration. So that's the resilience, that's the critical mass. This is what we call it in what I consider everyday language. And the question of existence or not, if it's an arbitrary game, we don't know. And I arranged it in increasing resilience because I think of profiles that are, okay, so for this talk, Nash equilibrium to me is the holy thing, it's the best thing in the world. The best, for this talk, I don't hold me to it forever, okay? So these are bad equilibrium because these are not Nash or very vague, very well, fragile Nash equilibrium. And as I go in, the holiest ones are dominant strategies, weakly dominant strategies. And then the ones next to it I will call nearly dominant. I will make use of them in a moment. And in between. So I was sitting yesterday at dinner, and we were talking about games on networks, and the only names that came to my mind where I wrote the slides I should have included. So if you look at centralized graph, so Yuval Harari, who's the writer of these evolutionary books, he makes a claim that dictatorial methods, governments are very unstable. And his point is very well made, because if you have a computer that's trying to hack the computer of the governor, it's very easy for a centralized network because he has to hack one computer. If you have to a decentralized system where everybody's making choices, say a choice of what language to speak based on their neighbors, then it's very hard to hack the system because everybody depends on half of the population. So you have to hack at least 50% of the population. So these are very low resilience, and these are very high resilience. This resilience here is 0, resilience here is 50% of the population. But let me now give you another theorem which is quite amazing and related to what you were talking about yesterday. So let me rewrite the graph, but let's look at it differently. So as we discussed, let's look at, for every game, let's look at the sigma that are of resilience greater than or equal to R for integer values, 0, 1, and so on. So greater than or equal to 0, we already commented, this is Nash equilibria. So I can look at all of this set of equilibrium and say these are the Nash equilibria. Another set that we are familiar with is the subset of Nash equilibrium that consists of dominant strategy and equilibrium when they exist. So that has a name. But if you look at all correspondence that satisfy 3 axioms, very similar to, not very different to what you were talking about yesterday, that is anonymous, you called it something else, I forget. Best response monotonic and satisfies the sure thing principle, then you get a theorem that says there are really n equilibrium concepts, starting from everything greater than 0 up to everything greater than or equal to n minus 1. These two have names. These are Nash equilibria, this equilibrium concept. This has a name, dominant strategy equilibrium, but the other ones in between are usually ignored, and they are in the paper, and the proof of this theorem that all of these are as legitimate in terms of these axioms as the other is a proof of this theorem, which is not trivial at all. So it's an axiomatization of the whole family of possible equilibria. And my point in this lecture now, the point that I want to make is the following. I'm going to look at strategic reasoning based on equilibria that are in the yellow set here, in the nearly dominant strategy equilibrium, and look at equilibrium that are in this pink set here, fragile Nash equilibrium. And I want to show you that I can make a lot of inference on the quality of the equilibria, the quality of the play, the implementability of this, based on this type of equilibrium without resorting to Nash, dominant, or any of this. In other words, my point is that it's important notions, intermediary notions. And the way I came to it is from Nicole Imorlica. She said, if you want to show that this equilibrium are valuable, show me an example in real life where this equilibrium will be useful, where Nash and dominant strategy and their refinements cannot, and that's what I want to show you today. Is it clear about? So my point is these intermediary ones that are usually ignored have valuable analytical ability for analysis of games. So let me look at the intermediary equilibrium. Let me look at nearly dominant strategy equilibrium and fragile Nash equilibrium. Fragile Nash equilibrium, I already had a definition. These are ones that one defector can make other people defect. It's not 0. It does not withstand even one defector. One defector can make others want to defect. And nearly dominant strategy means that it's not dominant that no matter what everybody does, you want to do it. It's nearly that if somebody plays this sigma equilibrium, then everybody else wants to play the sigma equilibrium. That's what you get if you read the definitions carefully. And it will help me, without loss of generality, to talk about strict nearly dominant equilibrium. I'll call them contagious. It's just easier to talk. So a strategy Psi is a nearly dominant strategy equilibrium without any restriction. If for any player J at any profile theta in which somebody play Xi, it's his best response for everybody to play Xi. But if instead of best response, I'll say strict best response, which is not going to interfere with any of my examples, then I'll call it contagious. And instead of saying instead of saying strict, nearly dominant strategy equilibrium, I would say contagious equilibrium. So let me show you some example of contagious equilibrium. So let's go back to the simple price game. Thank you. Simple price competition, everybody posting the price of one is a contagious equilibrium. Right? If Yuval posted the price 1, then I want to post the price 1. In that sense, it's contagious, right? So that's a very good property. It's not dominant because I need Yuval. I'm not saying it pays me to do 1 regardless. I'm saying if somebody does, then I want to post the price 1. And the same thing in bidding on a common value auction. If everybody bid 9 for something that's valued at 10, then the best response is to bid 9 also. And this goes well to many examples. I keep running into examples. If somebody goes to a demonstration, you want to join if it's contagious. If somebody applauds in a talk that you're not supposed to applaud, and you then applaud, the fact that somebody started applauding makes you want to applaud. These are all contagious equilibria. So contagious equilibria are very common, much more than dominant strategy equilibria. So if there are applications, it's good to know. So contagious implementation is better than dominant strategy implementation because it coincides with dominant strategy. Anything which is dominant strategy is a contagious strategy. So if I implement with contagious strategies, I do all the implementation that dominant strategy can do. But it does more because there are many situations where I can implement with things that are contagious but not dominant. So I have an implementation method. And here is a lemma that is very useful. Let me put it in the table form. Suppose I'm stealing not arbitrary game, but I'm looking at the game gamma that has a contagious profile Xi. And I now look again at all the resilience levels. If the game has a profile Xi, then no profiles exist in this intermediary category. Only Xi is in the dominant or nearly dominant profiles, and any profile other than Xi is bad. Is either zero resilience or no, not Nash. So that makes, if you have a profile with a contagious strategy, it's very powerful. And for implementation, it makes it very good because there are some of us who remember the implementation literature, some got prizes for that, because that means that it's an exact implementation, right? If I have a game, if I design a game gamma that has a contagious profile Xi, Xi is the only one that should be a contagious equilibrium to be played in this game. Everything else is ruled out, so you automatically get exact implementation in the terminology of this literature, I believe. So if I have more than 3 players, then there's no overlap between these 2 columns. Then we get a robust exact implementation of Xi if you can devise a game gamma that has Xi as a profile in it. And that includes pricing games, bidding games, first price auction bidding games, and many other examples that I mentioned before. So we already discussed the pricing game that they are implemented by, the pricing game implements the lowest prices, auctions implement the highest bids in a common value auctions. And my next example, and that's the main one I want to present, is that, okay, so I came to this because, is Nicole here? Nicole Imorlika was at Microsoft, and she said, if you claim that your equilibrium are so good and useful, show us an example. And I didn't have an example in mind, but then my wife is very liberal. We were listening to the pre-RICO trial in Georgia State, where Trump was being accused of manipulating the election, and the prosecutor over there decided to do a RICO-style trial to all of Trump and his co-defendants. And what was her name? Fannie Willis, she was the prosecutor. And Fannie Willis said she's going to do a RICO trial style trial because that should work well. She didn't know our theorem, but it works well because our theorem explains it anyhow. So let me now look at the 19-defendant pre-RICO trial game and show how it implements confessions. So it's like a prisoner's dilemma, but for N players RICO trial. So before I do that, let me refresh. So a prosecutor can have them play a pre-RICO trial gamma C with a hat, everybody confess. This is designated to make C in a hat contagious equilibrium, so it will become an exact implementation of full confession. So that was the motivating question. And when the motivation question was suggested to me, at first I said, well, let's try to implement it as a prisoner's dilemma. Let's try to make confession a dominant strategy. And Mark Sarsweit not only suggested the method, but proved right away that it's too demanding, cannot be done. Roger Myerson joined us a few years later, and he said, well, if dominant strategy doesn't exist, let's use Nash equilibrium to implement things. Let's do Nash implementation. But Nash implementation is not unique because there are other things that are Nash equilibrium. Roger's answer was, doesn't matter, the focal point of the truth will make them play Nash equilibrium, which is confession. But when you look at the prisoner's dilemma, there is another very strong focal point. Let's all deny. So that's the competing. So Nash implementation is too permissive. Denial is also a Nash equilibrium. So what we are looking here is we are going to look at contagious equilibrium, which is one less than dominant strategy, as I was arguing. And it's, let's call it in slang, sweet spot equilibrium in the sense that it exists unlike dominant strategy equilibrium. And moreover, it is more restrictive. It doesn't allow full denial. So it will give me an exact contagious implementation of full confession. So that's what we are going to do, as opposed to the standard methods at the time. So let me remind you that the prisoner's dilemma and see. So the two defendants are accused of this. There are two options, C and D. I'm going to reverse the order. C will be confess to the crime, and D will be deny, not cooperate and double quotes, okay? So confess and deny. And when confess, I added in green, that's very important, that you cannot just confess, you have to confess and prevent evidence that the crime was committed. Otherwise, a lot of innocent people confess. And the prosecutor can design what I said, can design a game in which confession is a contagious equilibrium. And the usual prisoner's dilemma we write like this. So it's a dominant strategy to confess in terms of jail time for both players. But in modern times, the judge says, if nobody confesses, if everybody denies, I'm getting them free out of jail card. So Giuliani was very happy. If nobody... So it's a positive, it's not just zero jail time if everybody denies. Everybody denies is better for player one than he confesses. So it's a 1 instead of a 0. But if you do this, then the prisoner's dilemma as is doesn't work because now this is a Nash equilibrium and this is also a Nash equilibrium. So we have a problem here. DD is a competitor to confess. But when I have more than 3 players, then contagiousy will come to the rescue and suggest this one rather than that one. So let me remind you, so the RICO trial, I have a mastermind who recruited the 19 co-defendants to turn over the elections in Georgia State. That's the story behind this example. And the judge says he will let them go free if nobody confesses. And here is the solution of the RICO trial that works with contagiousy. So she would ask everybody to confess or deny. And if everybody denies, everybody goes home free with a declaration of innocence. So it's a good positive payoff, one. If everybody confesses, everybody goes to jail for 5 years. But if some confess and some denies, then the judge will throw the book at the deniers because he has the confessors too. So the deniers will get a 10-year jail sentence. The confessors will be rewarded with a 0. So it's the same as the 2. But now, if you look at so we have no problems in terms of who knows what. The participants in the crime have common knowledge whether the crime was committed. But according to everything I said before, by the contagious implementation lemma, the contagious implementation is is a nearly dominant strategy. And if I look at the table version of this, oops. So everybody confessing is the only good equilibrium here, and every other way of trying to play it by the prisoners is bad equilibrium. Is either not Nash or fragile Nash. So this is the only one that is contagious equilibrium. And this is the game theoretic reasoning, the table I just showed you. And if you listen to CNN, then you look at Blitzrufer or Wolf Blitzer or whatever his name is. Here he was repeating exactly the definitions of the notions that we have here, which was very good because it shows to me that people understand what it is. And one thing that was surprising at the time when they asked the reporter, asked Fannie Willis, would she put all 19 co-defendants at trial at once? She said, of course. Said, why? Why would you want 19 people in the trial? And of course, the bigger the number, the more the contagious argument holds. So it's very important to put them all in trial. If she had 100 co-defendants, she would be even stronger, because everybody is afraid that somebody else will confess, and that's why they confess. And in the actual trial, this is the prosecutor, Fannie Willis. That's the picture. These people confessed. One more confessed. I didn't put the picture. The thing then failed because she got into an affair with the prosecutor, and they kicked her off the case, and they stopped it. But it was working just fine. And it's related to coalitions persuasion. If you like the language of persuasion rather than implementation, you can turn it into an example of a persuasion case. She first persuaded 2 people to confess, and then based on coalitional reasoning, it persuaded the others to confess. So it all worked well. And you can see the same with dictatorship now with Trump. Oh, I don't want to get into politics here. If a dictator wants to build a coalition, he can first build a small coalition, and then if these people have the incentive to go along with him, then maybe that will turn the rest of the population. So these kind of things. I don't have time, I'm going to stop, but there is a lot of interesting stuff about stag hunt games, why they are the cornerstones of stability in general. There is the relationship, why this is different from refinements, very different from refinements, and it captures new things. So I'm going to stop here if there are any questions.
So we have time for a couple of questions. I'll let you.
Yeah.
Very interesting concepts with resilience and the critical mass. One thing I'm thinking, the ranking between fragile Nash equilibrium to dominant strategy,
yes.
Nash equilibrium, right? One can think of different ranking.
Yes.
Because not every deviation is sort of the same.
Yes.
Maybe a fragile Nash equilibrium, but one deviation does not cause me a lot of bad payoffs.
Yes. So that's a very valid point that I've been presenting this a few times. This is a very common remark, and I agree with it. The only thing is, I don't know how to define resilience and critical mass differently, except that I have this theorem that gives me a theoretical justification. So that comforts me, and I would love to see some other, because I can think of many, many variations of the type you're suggesting. I don't know which is right, so I like it when there is a math theorem that tells me this is the scope of it. But it's a good question, I don't know. Yeah.
Okay. One more question.
Yeah. Eric.
So in your RICO,
Yeah.
in your RICO trial example, you showed that you can make confession into a contagious equilibrium. But you could also, if you wanted, make it a dominant strategy equilibrium to confess by saying that if one person confesses, she gets off.
Say it again? By saying what?
If one person confesses,
Yes.
she is rewarded by
We are rewarding them. We're giving them 0 jail time.
no, you can give her a reward for confessing.
Other than 5
Besides
years in
0,
jail,
yeah,
free.
you could get
I can make the reward out.
you could
There is an example at the end when I get to refinements and things like this, where I talk about, I can show you that Nash equilibrium is stupid if you allow me to modify the game. So I'm staying with the reasonable payoffs. But I could do various things like that, yes, yes.
well, the prosecutor has a lot of discretion over how to handle.
Yeah, but I want something that fits with formal game theory.
But this, I'm proposing something like
But
that.
is it equilibrium concept? Can you justify this equilibrium concept?
The equilibrium concept is dominant strategies.
You're saying you can construct a
You can
game?
construct a
Mark
game
Zuckerberg
which
would
has
be
a
very-
dominant strategy where you reward a single defector by
I should have come
giving
to the
them a
beginning.
bonus.
I should have come to the beginning of your lecture, I think.
Okay, so this sounds like a one.
Okay.
Let's be a good discussion.